So, hello everyone. Welcome to this third session on unification applied to security problems. The first talk will be given by Lynch on the security of cryptographic modes of operation. So, please go ahead.
Thank you. Good morning, everyone. So I'll talk about checking symbolic security of cryptographic modes of operation. This is a joint work with Chris Lynch. So this is the outline of my talk. So first, I'm gonna talk about the motivation of this work, and then I'll talk about what symbolic security is. And then after that, I will talk about an algorithm for checking symbolic security of modes of operation. In the interest of time, I'm gonna simplify things a little bit. So what I'll talk about doesn't correspond exactly to what's in the paper, but of course the ideas are the same. If we wanna encrypt a message, then the basic building block is called a block cipher, which is a way of encrypting a single block. And the most commonly used block cipher is called AES, which can encrypt a message of 128 bits. If we have a message of multiple blocks, then we should use a mode of operation. And there are many modes of operation. For example, there are Cipher Feedback mode, there's Cipher block chaining, and many more. So here's Cipher block chaining. In this example, we have 3 plaintext blocks. In order to encrypt a particular plaintext block, we take the previous ciphertext block, we XOR it with the current ciphertext block, and then we apply block cipher. So here, PI means the ICE plaintext block, and CI means the ICE ciphertext block. But in order to encrypt the first plaintext block, we have to define what a zeros ciphertext block means. So the zeros ciphertext block is defined to be R, which is some initialization vector. So it's a randomly generated block. So here's another example, Cipher Feedback mode. So again, we have 3 plaintext blocks. In order to encrypt a particular block, we take its previous ciphertext block, we apply block cipher, and then we XOR the result with the current plaintext block. And again, as a special case, C0 is defined to be R, which is the initialization vector. So there are many cryptographic modes of operation, and we can ask which of them are secure. Can we check security automatically, or can we even automatically synthesize secure modes of operation? And a solution would be to reason about security of modes of operation symbolically and automatically. And I should say that the general framework of reasoning about symbolic security is laid out by Cassie Meadows. And what we did is that we came up with an algorithm for checking symbolic security. So as a first step of checking symbolic security, we should model modes of operation symbolically. So here are the notations that I use. So F denotes a block cipher, and R denotes a randomly generated block. XI denotes the ICE plaintext block, which is a variable, and CI denotes the ICE ciphertext block, and the 0 denotes a block of all zeros. So using these notations, cipher block chaining can be modeled as CI is f of CI minus 1 XORed with XI, and C0 is R. And then there's this notion of symbolic history. So a symbolic history is essentially an interaction between an honest party and an adversary. So sometimes the honest party is also referred to as the oracle because it responds to queries from the adversary. And the interaction goes as follows. So first, the oracle sends to the adversary C0, and then the adversary sends to the oracle X1, which is the first plain text block, and then the oracle responds with C1 and so on. So if we look at cipher block chaining mode, and if we consider this sequence C0, X1, C1, X2, and so on, so essentially all the terms are listed in the order that they are generated. And we can unfold each of the CIs by this definition. So by this definition, C0 is R, and C1 is f of R XORed with X1, and so on. So we can unfold all of the CIs in this sequence and get a symbolic history. There's also this notion of computable substitution. So if we consider this symbolic history of CBC mode, all the variables, all of the XIs can be instantiated. And here's an example of a good instantiation. So if we map X1 to be R and X2 to be f of 0, that's a good instantiation, because by the time the adversary tries to generate X1, which is the first plain text block, the adversary already knows R. And by the time the adversary tries to generate X2, the adversary knows f of R XORed with X1, but we can set X1 to be R. So f of R XORed with R is f of 0. And if we map X1 to be f of R, X2 to be f of R, that's a bad instantiation, because by the time the adversary tries to generate X1, the adversary only knows R, but the adversary doesn't know how to do the encryption because it doesn't have the key. So the adversary doesn't know how to compute f of R by the time it tries to generate X1. So in general, each Xi can be instantiated by the XOR of 0 or more CJs that comes before Xi. So if that constraint is satisfied, then we call that substitution a computable substitution. So here's the definition of symbolic security. Essentially, this definition says a mode of operation is symbolically secure if it doesn't admit any symbolic history where there's a subsequence of ciphertext blocks in H such that their XOR is 0 under that computable substitution. And the intuition is if a mode of operation is symbolically secure, then all of the ciphertext blocks are as good as randomly generated blocks. So this sequence of real interaction is indistinguishable from this sequence where all of the CIs are replaced by randomly generated blocks. So as an example, cipher block chaining is not symbolically secure because first we can find a computable substitution sigma where X1 goes to R, X2 goes to f of 0, as we discussed earlier, is a computable substitution. So under that computable substitution, the first ciphertext block, the XOR of the first ciphertext block and the second ciphertext block becomes 0. Because so X1 goes to R, so the first ciphertext block becomes f of 0, and we can check that under this substitution, the second ciphertext block also becomes f of 0. So the result is 0 under that substitution. So here's another example. Cipher feedback mode is symbolically secure according to this definition But at this point, it's not obvious at all why this is the case. So that brings us to the question of how we should check symbolic security. So the overall idea is that we introduce this other property called the uniqueness property, which implies symbolic security, and we give an algorithm for checking the uniqueness property. The definition of the uniqueness property is a bit technical. So first, let me motivate this definition. Suppose that we have a model of operation M where Ci is f of Ti XORed with Xi, and C0 is R. So the symbolic history would be this particular sequence, right? So we have R X1, f of T1 XORed with X1, and so on. And the claim is if all of the F-rooted summands in the history are unique up to computable substitutions, then M is symbolically secure. So here's the idea of the proof. So let's consider any computable substitution. By definition, each xi can only be the XOR of some previous F-rooted summands. And now, if we compute the XOR of C1 through Cn under that computable substitution sigma, then by definition, Ci is the XOR of f of Ti and Xi. So we can group all the F-rooted summands together, and we can group all of the variables together. Because we applied this substitution sigma, some terms may be unifiable and goes away. But the claim is f of Tn, which is the last F-rooted summand, cannot go away. It cannot go away for two reasons. First, we assumed that all the F-rooted terms are unique. Therefore, no F-rooted term can make f of Tn go away. Second, we only consider computable substitution, where all of the variables can be mapped to the XOR of some previous F-rooted terms. But since f of Tn is the last F-rooted term, so no variable can make f of Tn go away. Therefore, f of Tn remains in the result of the XOR. Therefore, the result of the XOR cannot be zero. So symbolic security is satisfied. And essentially, the definition of the uniqueness properties says all of the F-rooted summands in the symbolic history should be unique up to computable substitutions. So here's the formal definition. It says, consider any symbolic history. M satisfies the uniqueness property if all of the F-rooted summands in the symbolic history are unique. And we have a theorem that says uniqueness property implies symbolic security. So the next question is, how should we check the uniqueness property? So here's the overview. We assume that two F-rooted summands are the first or the earliest pair of unifiable terms in the symbolic history. And then we try to derive a contradiction using some inference rules, where each rule is of the following form. So the premise is a set of equations, and the conclusion is also a set of equations. And the semantics is that if at least one of the equations in the premise hold, then at least one equation in the conclusion must hold. So essentially, each equation represents a particular possibility, and the set of all equations represents the set of all possibilities. If we want to derive a contradiction, we should try to make the set an empty set. So if we can do that, then that means contradiction is derived, and the uniqueness property is satisfied. Therefore, symbolic security is also satisfied. But if we cannot derive a contradiction, then we don't know. So this method is sound but incomplete. And fundamentally, the problem of checking symbolic security is undecidable in general. So we can't hope to achieve all of the three properties: soundness, completeness, and termination. So this method is incomplete. So here's an example. So let's consider Cipher feedback mode, where Ci is defined to be f of Ci minus 1 XORed with Xi. So the first step is that we take two different ciphertext blocks, Ci and Cj. We take the f-rooted summand of Ci, which is f of Ci minus 1, and we take the f-rooted summand of Cj, which is f of Cj minus 1. We assume that they are the first pair of unifiable f-rooted summands. And then we apply some inference rules. So we start with our assumption that f of Ci minus 1 and f of Cj minus 1 are unifiable. And the first rule that we apply is called peak f. So in this particular case, the peak f rule looks a lot like the standard decomposition rule, but it's more general than that, as I'm going to show you later on. So if we apply the rule, then we get Ci minus 1 XORed with Cj minus 1 is 0. And the second rule that we apply is called elim C. So essentially, it says it's impossible that these two terms are unifiable. And the argument is very similar to the argument that the uniqueness property implies symbolic security. So essentially, some f-rooted terms can't go away, assuming that f of Ci minus 1 and f of Cj minus 1 are the first pair of unifiable terms, and assuming that we only consider computable substitutions. So at this point, we derived the empty set, which means that we derived a contradiction. Therefore, the uniqueness property is satisfied and symbolic security is also satisfied.
Sorry to interrupt you. Yeah, there are 2 minutes left, so try to conclude soon.
Okay, thank you. So here are the inference rules. We have elim f, which says if we have f-rooted term equals 0, then that's impossible. And the elim C says if we have the XOR of Cm and Cn equals 0, that's also impossible. And the occurs check is standard. We have three other rules. Pick f. So essentially, if we have the XOR of a bunch of f-rooted terms, if the XOR is 0, then all of the f-rooted terms must go away. In particular, f of tk, where t is chosen non-deterministically, must go away. And we just list all the possibilities that f of tk can go away in the conclusion. So f of tk can go away if tk is unifiable with t1, or if it's unifiable with t2, and so on. So that's the peak f rule. And the peak c rule says if we have Cm XORed with a bunch of f-rooted terms, then essentially we can first unfold Cm and apply the peak f rule under some condition. So let me skip peak fail. So here's the algorithm. Essentially, we just check for all possible pair of f-rooted summands. We get a contradiction. If we can do that, then that means symbolic security is satisfied. Otherwise, we don't know. So here's the conclusion. We propose a method for checking symbolic security. Because the problem is undecidable in general, our method is sound, terminating but incomplete. We can use this method to automatically synthesize modes of operation. So we can do this in 2 steps. first we randomly generate some candidate mass of operation, and then we use our method to filter out insecure ones. Okay, thank you. So are there any questions?
Yeah, thanks a lot for your talk. It was a very nice talk. Other questions? Please try to raise your hand if you have any question. Yeah, I see a clap. Yeah, congratulations for the nice talk. So I would have a question with respect to the XOR unification you have to use in your framework. Could you use off-the-shelf XOR unification procedure, or do you have to adapt it?
So I need to adapt the standard one because here we only consider computable substitution.
Okay, so you have to take into account the history and the fact that you are looking for computable solutions.
Yes.
Okay. So you cannot use directly off-the-shelf XOR unification procedure.
Right.
Okay. Okay. And another question. I think that you have introduced a specific mode of encryption in your talk, and my question was: does it satisfy the uniqueness property? Is it an example where the uniqueness property does hold?
Yes. So for the
CFB mode,
Cipher Feedback mode, that property is satisfied. The uniqueness property and the symbolic security are both satisfied. But for Cipher blockchaining, the properties are not satisfied.
But does it mean that you have already several examples showing that this sufficient condition is, let's say, good enough to conclude about the security of the mode of encryption?
Yes, so we introduced this uniqueness property. It implies symbolic security. Yeah.
But do you have other examples of mode of encryptions that satisfy this property?
Yes, we have some other examples. So for this Cipher Feedback mode, this property is satisfied. But we so in our paper, I think we have another example.
Okay. Okay, good. So you mean, do you think that you have the right condition to check several mode of encryptions?
Yeah.
Are you still looking for other sufficient conditions?
That's a good question. So the thing is, it's hard to check symbolic security directly. So what we did is that we came up with this other property, which is the uniqueness property, and we check the uniqueness property. But it could be the case that there are some other sufficient condition for symbolic security, and it's easier to check that other property. But right now we just check the uniqueness property.
Okay, good. Thank you. Thanks a lot. So if there are no more questions, I think that we will have to move to the next talk, and so to the next backstage for us. So
okay,
let me.
Here, do not join the discussion room, since you will miss Hai.